Good morning, everyone. My name is Venu, and I'm a results-driven IT professional with over 12 years of expertise in software industry. My career has been dedicated to ensuring the reliability, performance, and compliance of enterprise applications across critical industries, including telecommunications and healthcare. Currently, as a lead technician at Spectrum, I spearhead software initiatives for billing systems, validate SOAP REST APIs, and design UI UX workflows leveraging tools like Postman, SQL, NoSQL databases, and automation frameworks. My work directly supports CI/CD pipeline and agile teams, ensuring seamless integration and high-impact solutions. Previously, I led software efforts for Medicaid chip systems under Department of Health and Human Services for South Carolina and IBM, where I ensured HIPAA compliance and federal data hub integrations, demonstrating my depth and regularity domains. With proficiency in automation, defect tracking, and cross-functional collaborations, I bridge technical and business needs to deliver robust software solutions. My portfolio includes 200 plus technical documentation and 1000 plus automation regression suites and scalable testing strategies that reduce the risk and accelerate delivery. And I had a master's degree from the University of New Haven, and I'm passionate about mentoring teams and driving innovation in software practices. I'm excited to share my insights from experience and explore how we can solve the complex challenges together. This is the this is about building Rust-powered AI for telecom from reactive to predictive systems. Today, as we are driving into transformative shift into telecommunications, where Rust-powered AI is turning reactive network management into proactive, predictive systems. Imagine a world where outages are predicted and prevented before even customers notice. This isn't science fiction, it's happening right now. The Rust is the unsung hero make it possible where cutting edge technologies meets real world impact. Let's explore how it's revolutionary is unfolding it. Yeah. Today's agenda is how here's our today's agenda. The telecom challenge. Why today's break fix model is broken. The second one, the Rust. How a language designed for safety and speed solves decades old the real world implementations from anomaly detection to predicting cell tower failures. And now about the integration challenges, the gritty reality of merging AI with legacy systems. The fifth one is future roadmap. How to phase this into operations. Why does this even matter? Because every minute of downtime costs telecom communication an average of $5,600 per minute. The stakes are high and the solution is here. The telecom challenges today. So let's confront the harsh reality of today's networks. 72% fault detection means 28% of the issues slip through, silently degrading the services of the telecommunications. 3.7 hours for MTTR. Picture a hospital losing connectivity during an emergency. Every minute counts. 80% of today's are planned outages, where like mechanics changing on a schedule, where the engine is already overheating, all kinds of things, which is the root cause. The fragmented tools. Engineers today, tools are between 8 to 12 systems, wasting 20 plus hours weekly on manual correlation. Reactive mindset alerts fire after customers complain. I worked with an European carrier last year who discovered that 40% of their sudden outages had clear procedures like memory leaks or temperature spikes visible in the telemetry data days in advance, but without AI, no one connected the dots. Now the cost is that's the cost of reactivity. Why Rust for telecommunication AI? Rust isn't just another language, it's a paradigm shift. Let's break down why it is a perfect for telecommunication AI. The memory safety. Garbage collectors in Java Python causes latency spikes like 200 milliseconds pauses. In telecommunication industry, thus enough to miss a critical failure signal. The Rust ownerships model eliminates this one. The real world example is a tier one carrier company reduced telemetry processing from 150 milliseconds to milliseconds by switching it to Rust. The features of concurrency. Traditional threading leads to race conditions. A Rust compiler enforces thread safety. A case study saying that the processing 10 million data points per second across 50 threads with zero deadlocks. The zero cost abstractions for this particular thing. C++ level speeding without crashes, but benchmark of the Rust prices about 100 GB of network lags in 22 seconds versus Python's 8 minutes. That is where the real difference is. The strong type system, the compile time checks, caught a critical API mismatch in a billing system integration that would cost a 2 million in NRS changes. A fun fact about this whole thing is most loved language on Stack Overflow it's been for over 7 8 years. Why? Because it's runtime disasters in compile time errors. For telecommunication, that's the difference between a hiccup and a headline marking making outages. This is about the performance metrics versus the traditional implementation. Let's talk the numbers. The slide compares Rust powered AI to the legacy systems. The fault detection 92% versus 72% catching. There's 20% more issues means fewer midnight emergencies. MTTR 47 minutes versus 3.7 hours. That's a 3 hour save per incident. The 3 hour save per incident. Customer churn down by 1.2%, which translate to $8 million in a year for a mid-sized carrier. One client said, why not just scale our existing Python system? As we tested it, it's 5,000 requests per second. Their Python service crashed. But the Rust handled 85,000 requests per second on the same hardware. Sometimes the tool is bottleneck. Rust powered AI algorithms. This is about this thing. The two algorithms are the game changers. The first one is isolation forest. How it works is randomly isolates anomalies instead of profiling normal behavior. Think it's like a folding haystack and eliminating hay. It's detecting as DDoS attacks in 3 seconds by spotting irregular traffic patterns. LSTMs. These neural networks predict failures by remembering patterns over time. So this is the main key thing in this whole thing. An example, a cell tower power supplies typically degrades over 6 months. The LSTM flagged once failing for every 2 weeks, saving almost a 200K in replacement costs. See the real fear. And the whole kicker is the Rust speeds let us run these models in line with data streams. No batch processing. Python would need 15 times more servers to keep up with this 500K a year on this cloud assets cost has been saved, particularly using this Rust technology, Rust language. This slide 7 a case study about predictive maintenance of the cell tower. Let's zoom into North American carrier results. The 25 TB per day of data from 5,000 cell towers is equivalent to 10 years of Netflix streaming. The LSTM predictions the flagged falling hardware 14 days in advance with 89% accuracy results, which in turn result to 60% fewer outages and 42% fewer truck rolls, saving an average of $1.2 million in a year. This is the best part where the NOC team went from firefighting to strategic planning. One engineer told me that finally feel like I'm preventing disasters, not clearing them up. That's a cultural transformation in this telecom industry. The next slide shows about the unified platform architecture in this particular thing. So here is how the sausage gets made. So collection adapters. Rust normalizes the data from 8 to 12 legacy systems into a unified format. Then the message bus zero copy design moves a 5 TB in an hour with the overhead of pass post-it note. So explainability layer where the engineers get plain English insights like transformer 42 fails 70% of the time during peak loads. Now we can notice that in 1990s eras, a Sonnet system or Rust FFI, the foreign function interface, let us wrap it C code safety, no rewrite needed. The client called it a time machine for their stacks. That's back in 1990s era. These are implementation challenges. So no transformation in painless. So it's always integration challenges are always there. Here, how we can tackle these hurdles. So the legacy integration. So use Rust FFI to wrap COBOL billing systems. There's a tip there. First testing caught a memory leak that would crash production. And next is the data quality. Rust scripts autofill missing timestamps using Markov chains. And the next one is the black box fear. Added to Y button next to every AI alert. That's how it is. Showing the top three contributing factors. A CTO once asked me, how could I sell this to my board? The answer is straightforward. Straightforward. Start with the pilot on a non-critical towers. When they saw 40% reduction in outages, the budget approval took 10 minutes. It just took 10 minutes. Now, the next one is about the workflow evolution of the operational roles. So, AI won't replace any engineers. It redefines the roles before the manual log scripting for the outage triage. After this one, the training models and turning algorithms. Once a team automated 80% of the repetitive tasks instead of layoffs, they upskill everyone. Their job satisfaction score jumped 30%. Happiness engineers fix problems faster than the regular one. The next slide is about the implementation roadmap of particularly there are four steps in this implementation. The phase one is about the data foundation. Deploy Rust collectors. It's a instrumental like one tower type first example 4G only. The phase two is anomaly detection. Use isolation forests to find quick wins. Its example is a power supplies, a faulty power supplies. The phase three is predictive models, training LSTMs on historical failures caution. Start with the non-safety critical systems. And coming to the phase four is automation. Auto restart failed nodes without an even human oversight. Client is an example. A client faced this over 18 months by 18 months, but by 6, their ROI was 2.3 million. From reduced truck roll alone, the board, the fast truck, the whole thing. The next one is thank you. Good.